Okay, today, guys, we start memory management. Just want to make sure that the memory management or memory manager. Yeah, that's clear enough, right? The writing, you can see, that's wonderful. Okay. So probably memory management is probably the most difficult part of the operating system managers. The rest of them are so simple and easy. So make sure you get this part, the memory management, this week and next week. After that, you can relax. Right, memory manager. We're gonna start with the first system that they used, and we walk it up to the existing systems that we have today on computers. So first system they used, they called it the fixed memory management system. Number one, fixed partition memory management system. Well, this is the first system, and it's the easiest system. So let's get a few things first straight. Every program, in order for it to execute, you should know this by now, it must be loaded into main memory. Why? Because the CPU executes one line at a time or one instruction at a time, and you need to give it to the CPU so fast. The CPU can execute 1 million instructions at least. They get them faster and faster. So 1 million command is done by the CPU. And the command has to be brought into the CPU. It's like a machine. Comes in, you hit it, and then bring the next one, hit. So one command at a time. So you need to be able to supply also those commands, and the commands are the lines of the program. Your program or your process has many instructions. Guys, if you need to talk, please go there, finish your talk, and come back in here. Right. So, but memory has been historically very difficult to manufacture, especially 60 years ago, and very scarce, like very little memory is available, and it's needed. Computers in the back days, in the old days, they had very, very little memory, something like 64,000 bytes. Now we have computers that have gigabytes, like 16, 32, 64 or more. So just you can imagine, very, very small amount of memory, and it needs to be used quite effectively. And also, in the old days, you needed to write very short programs in order to run. Otherwise, you have no chance of executing that program. It must go in memory. So, and in the older days, this is the way they've done it. They said, listen, we have this amount of memory, and everybody knows what memory is. It's just millions of switches. They're very simple, like millions of bits. And every bit is like a switch, like an electric switch. It's either on or off. That's what memory is like, and that's what the computer understands. That's the only thing, really, computers can see. They can look at a switch and they say, okay, you can tell them to switch it on or off. That's what a computer can do. But also a computer can identify or look at a switch and recognize, is that on or off? That's really mostly what computers are good at. But in order to execute a program, we need to put that program in memory, and everything written is written now in binary. We write it in English or whatever programming language, but it's always translated into binary to go into memory. or to be stored on a hard disk. Everything is stored in ones and zeros. And ones and zeros are just the switch is on or off. That's what it means. It's easier for us to say 1 and 0 instead of saying the switch is on or the switch is off. But anyway, there are millions of those switches, and they're grouped in bytes. So instead of counting and say, okay, we have 16 million bits, we can say, okay, divide them by 8, and we have whatever, 1,000 bytes. So it's easier for us because we can put a character in a byte. So every single byte can take a character, every 2 bytes we can put a number in them. And sometimes we need 4 bytes, whatever. Those systems are later on. But we are not here to discuss those systems. So we say, okay, we have memory. And memory is all numbered. Byte number 0, byte number 1, 2, 3, all the way to whatever maximum number of bytes we have. So all memory in there, like the brain cells that you have, are all numbered from 0 to the maximum number. That's what memory switches in the computer. We have them numbered from 0 to the maximum number. Now, for every program to run, we need to upload it into memory. But remember, the operating system itself is just program, software, as well as the hardware, but it controls the hardware. We control it by the software. So the operating system is a lot of programs. So first, and they are loaded up first into memory. So there's usually something else to remember is that memory is volatile memory. The word volatile means if it loses power, it loses the information in it. All the switches go off, or they take a random place. There's no power. So anytime we had any information in there, and if we cut power off, all the information is gone. So, you have a question?
Yes. Can you say again what volatile memory means?
Volatile memory, I just said it. It means if power is switched off, the content of the memory is lost. Okay? You will be doing a course called hardware, and that's where you'll learn more about memory. But I'm giving you at least the minimum amount of information that you need to know to carry on. So, all memory is there. This is main memory, and we need to upload the information in there. First thing that gets loaded is called the operating system. All the programs that make up the operating system, or the essential part of the operating system. And what do we call that essential part of the operating system?
Kernel.
Okay, I was going to pick a student, but that's fine. Kernel is good. So it depends on how big the operating system is. It's the kernel, the essential part that we want to keep in main memory. Because if it's needed, it works immediately. If it's not in main memory and you have to upload it from the hard disk, it'll take few seconds from the hard disk. Few seconds is like weeks or months or years to us. So that's why we need everything in main memory to work very quick. But whatever it is, the operating system is uploaded, and it's better to upload. It's better for the operating system to be small. So if you look at an operating system now with all the software in it, and if you can write the same functions but in shorter code, you'll be brilliant. Computer companies would love you. Operating system companies, because that means less memory is needed by the operating system. But the operating system sits there first. First thing that's uploaded is the operating system, software for the operating system. And the operating system will mark this address. So all addresses from 0, let's just say now, for now, up to address 4000, 4K. It's probably a lot more, but for now, let's just say that. That belongs to the operating system. Nobody is allowed to go there. No other user program is allowed to go there. Now, the fixed partitioning, how are we going to manage programs and put them in memory? So what they decided first, they said, let's divide the rest of memory into variable sizes blocks. So why? Because, for example, if we just split it into equal size, let's say the rest of the memory, let's say, is, just for argument's sake, 100K. So here's 25K, 25K, 25K memory. That means 25,000 bytes, for example. It could be 250,000, doesn't matter. But now we split it into equal size parts. Now, if we have a big program that wants to run that's size 35, we will not be able to fit it into memory. So what they did, they left some parts that are much bigger and some parts that are much smaller, so we can accommodate large programs and small programs. For example, we say we'll have 20K memory, 20K, another part that's 20K, and then we have maybe 80K, and then maybe here we have 200K. So we split memory into different blocks. Some of them are small and some of them are large. It's just like the rooms in a hotel. I always kind of describe or use, for an example, memory, I use rooms in a hotel. Maybe some rooms are, you go to a hotel, they might have one bedrooms or rooms, and double bed, or maybe 4 bed. They're different size rooms. So if we get one person coming on their own, they want a room, we can put them in the single bed room. And if we get 3 people coming in, we can fit them into the 4 bed. So we can fit different based on the requirements of the customers that come in. So this is exactly what happens with operating systems. That's basically what it does. So program number 1 comes in, for example, here's job number 1 or process number 1. Once it comes in, it hasn't come into memory yet. The user double-clicked and said, okay, run this program. So the operating system will call the memory manager and say, listen, we have a program that needs to be accommodated. We're going to execute this program. So first thing the memory manager looks at, how big is this program? Let's say this program is 65K. The program has 65,000 bytes or 65,000 lines of code or whatever it is of certain size. So the memory manager will go through the blocks that it has, just like in a hotel. We have this room, it's free, but that's 20K. That's another 20K, that's too small. This program is 65 until we find 80K. Here's a block that can fit that program. So we put program 1 in there, and here it is, program 1 is sitting in there. Even though this is an 80,000 bytes, and the program is only 65. It will not fill it, but it will fit in it and will execute. Okay, so that's how it works. Then we get maybe another program number 2 comes in. And let's say it's 150K, slightly bigger. So we go through and we look and we say, here's this one here is 200K, so that will fit in there in this block. So 150K is sitting in a 200K block. The next program that comes in, program number 3, let's say it's 18K. Where do you think the operating system will locate this program? Which block? Block 1, 2, 3, 4, 5, 6, or 7, or 8? Program, yeah, block number 1. That's perfect, because it will fit in there. That's a nice way of doing it. That's if we decide we'll give every program the smallest block that it should fit in, which is the most efficient way of doing it. Provided there is no other program is at the moment occupying that block. Like in a hotel, if there's a customer in room number 12 and another customer comes in, you don't put them in room 12 as well. You know, that's busy. That room is occupied. It's booked. Somebody's using it. And in order to do this, they do what they do in hotels. What the person at reception is, but now we do this. So this is what your program would be doing. The program, look, that manages. So we'll probably have a table here. First, all these blocks in memory. Block number 1, 2, 3, 4, 5, 6, 7, and all that. And each one of them, the size of the block, for example, this is 20K, 20K, whatever it is. The other one's 20, 80, 80, and 200 and 200. So all the programs are mentioned in this table. And is this busy or free? Let's say the state of this room or block. So we might mark them all as free at the start, but this one we know somebody's using this one. So this is busy. The rest of them are free. The 81 is busy. The first 81 is busy. And the first 200 one is busy. The rest of them are free. So allocation, when we say the memory manager will allocate memory to a program, what do we mean? When a program comes in, let's say program number 4 now arrives, program number 4, and it says it needs, for example, 60K. So this is what the memory manager will do. This is the allocation part. It will go look through the table for a block that will fit this program. This program needs 60K. So to look for a block that's 60K or bigger, and there is an 81, but also free. This one is busy. So we know there's another program using this. So it will find another one. Well, here's another program that's 80K and it's free. So it will put this program into this block. There it is. Now program number 4 is sitting here and it's only 60K, even though the block itself is 80K. And it will go to this party and mark it as B, busy. And we call that allocation. So now you know what's involved in the allocation. The program request comes in, the memory manager checks what size it is, and it goes to the table. It has a table of all the blocks, just like a table of all the rooms in a hotel, and it'll look for a block that will accommodate, that's large enough to accommodate this program, and at the same time it's free and it's marked as being busy. So now the program is put there. So the program code goes in there. And now we know exactly where does this memory start. So part of this table as well as the blocks table, it says where's the starting address of this in memory. So every block we know where it is, just like every room in a hotel, they tell you this room is on the 3rd floor, number 5. So you need to know is at the exact location. Same with this block. Where is this block? This block starts at 4,000. Remember, the first block starts at 4,000. And it's 20,000 bytes long. So it ends at 4,019, for example, because the next block will start at 4,020. You understand? So everyone will start at the end of the next one. So it's how big it's like this one. If I say, okay, those 2 blocks, I'm going to put them in separate sections. So this one finishes here. So that's the address of this one. This starts at block number 3. And if it's size 2, that means the next block will start here at number 5. So you need the starting location or address of every block, where it is, how big it is, and is it busy or free. So that's how it's kept. Same in a hotel. They need to keep a table of every room in the hotel, how big it is, like how many beds are in it, and where it is in the hotel, and also is it busy or free. And that's how a memory manager, the first memory manager they introduced, that's how it works. And it works beautiful. It has little advantages and it has disadvantages. Anybody can see any issues or problems or inefficiencies with this? Because it worked. There's no problem of not working. It's very simple to work, and that's one of its advantages. Very simple, very easy program that any programmer can write. A program comes in, I need so much, that's how big the program is. It needs 45K, simple. I go through the table, find any block that will fit 45 or bigger, and if it's free, I'll mark it as busy, and I put that program in it. And let me now when a program finish, let's imagine a program is finished, then the operating system will tell the memory manager, by the way, this program number, whatever it is, let me pick this program here. Program number 1 is finished. So the memory manager should go to that block. It's like a customer leaving in a hotel. Room number 130, the customer has left. So we go to the table here, look for that room, and instead of being busy, so that's that one there. That's where program 1 is actually sitting there. Normally here we'll have even the name of the programs now in each room. So in fact, program number 1 here, but that's what we identified by the block, and it used to be busy. Now we mark it as being free. That's the only thing you do, and this is called deallocation. Deallocation, that means we've taken away the block of memory from this program. We didn't even have to go to the program code and overwrite it or remove it or wipe it off. It doesn't matter, because when we give this memory to another program, we'll overwrite the new program will be written here. But all we did is just mark this block as being free. So now it's available to maybe a new program that comes in. So this is how memory is allocated and how it's deallocated. So simple. In fact, the deallocation is even simpler. All you have to do is go to that block, mark it as being free, and that's the end. Now we can, if another program comes in, we can allocate that part of memory to that program. Okay, so let's look at how good this program is. In fact, any issues? Does anybody can see any problems with this system yet?
Yeah, there is some spare space still available in blocks because not every program fits the exact amount of.
Some spare space. Where would that space be? Let's take this example here. Thank you. Program number 4. Program number 4 needs 60 kilobytes. That's how big the program is. And we look in memory and we found, there it is, we put it in a block that's 80K. So there's some space left that's not needed. It's like when there's 3 of you, you go to a hotel and he says, you ask for a room with 3 beds, you say, we don't have a room with 3 beds. They're all busy. But to have a room with 5 beds, you have to pay for it. You have to pay for 5 beds, but only 3 of you. So you're using, there's 2 spare beds in the room that you don't need. So that's very inefficient. And if you have that room and one customer comes in that they say they need 1 bed, they can't put them in the same room. That's it. So if we get a small program that's only 5K, we cannot. Okay, so this part here only you need 60K, but 80K, the whole thing is 80. So there's 20K spare. If a small program comes in that's only 5K, we can't put it there because that's whole one block is given to one program. They cannot share the same space of memory.
Are you doing more advanced systems?
Oh yeah, advanced system. That's why we're looking for problems to improve them and eliminate them.
Okay.
So that's the first, a major issue of this system. And they call this system here, this small space that's left, they call it fragmentation. And it became later on to be called internal fragmentation. So we will call it now internal fragmentation. Why do they call it internal fragmentation? Because we gave you a block that belongs to you now, and there is space in it. There's fragment in it that you don't need, but it's yours. It belongs to you, and that's why they call it internal fragmentation. as we'll later on we'll see, there's another kind of fragmentation. So this system, the fixed partitioning memory management system, suffers from one issue, and that's called one problem. It's called internal fragmentation. So if you're asked, how does internal fragmentation happen? A quick and short and maybe precise answer, it says if a program is allocated a block, a bigger block than it needs. That would be a perfect answer, short and specific. It's like if a program, and if you want to make it, even if you can't explain it, give an example. You say, if we have a block, for example, size 100, we have a program size 80 or 70. If we give this free block of 100 to a program that's only needs 70, that means the rest of the 30K we call internal fragmentation. Okay, so if you are asked what's internal fragmentation, you can explain it or you can describe it by an example, just to be perfect. So that's a major issue. And
Fragmentation is the name of this spare.
the extra space, the spare space, yeah. The extra space that anybody can have once they are allocated space and they don't need it. It's space that's allocated to you, but you don't really need it. And no one else can use. So we call this internal fragmentation. Now, let me have another simple example. Here's all the operating system code is always sitting there. And we have, for example, a few blocks of memory. Let's say this is 40K, 40K, 80, and 200. Okay, so look at this operation. So this is a dynamic thing that keeps happening. Let's say we get program number 1. I'll just ask you the question, you tell me which block will we put it in. So we have 4 blocks, block 1, 2, 3, 4. Program number 1 comes in. And it needs 100 kilobyte. Okay, which block shall we put this program that needs 100 kilobyte? Which block it will be allocated in? Block 4. So block 4 is busy with program number 1. That's great. Now, program number 2 comes in. It needs 30K. Maybe I should have put this one 20 and 40 just so. Yeah, it doesn't matter, but it's just so to differentiate. So, program number 2, which block will it go into? Yeah, block number 2, program 2, that's 30K. And now it's busy. So this is busy and that's busy. Now we got 15. Now we got program number 4, 18. Where would we allocate program 4? Needs 18K. 3, because these are busy. And it will fit in this one. So program number 4 is 18. And there's a lot of internal fragmentation in this one, right? A lot of space. They all had a bit of internal fragmentation. Right. Let's say then program number 2, this program 1 is finished. So deallocation happens. Now this is free. This is the only block that's free now. Another program comes in, program number 5. Let's say it also needs 10K. There's nowhere to put it except in this space here. So this is busy with program number 5, 10K. Let's say program number 2 finished. Program number 2 ended. So this block here becomes free. Is it through? 2, yeah. Now we get another program that's 60K. We cannot allocate it. So they have to sit and wait. So program number 6 needs 60K. We say, wait, you can't execute. Another program comes in that's a little bit smaller, that can fit in 40. So this one needs 33K. It will go there. So that's busy. And this one is still waiting for a big block. So after a little while, you can find that there are programs that you cannot execute, or they take longer time, or maybe very small programs end in getting very large free block. So it's not very efficient. Some programs cannot be executed. Some programs use a lot of memory very inefficiently. So they try to improve that. And instead of the fixed partitioning system, a new system came up, and it's called the dynamic partitioning system. The dynamic partitioning memory management system. And with every system, if you are asked to describe that system, you have to give those 3 situations. At the start, what happens? What does the memory manager do before any program comes in? And then what happens when a program comes in, and what happens when a program leaves, like the allocation and deallocation. So this is simple enough. Let's look at the dynamic partitioning. This is at the start. First, there is part of the memory that's allocated to the operating system. Let me go back to the fixed partition just to show you one little issue that sometimes happens. If you have the code here and a program starts executing, every reference to memory is translated into an address. For example, guys, if we say this program says I have variable x here and put 5 in it, it has to be within this part of memory, in the space allocated to this program. But if this program tries to change a memory location that belongs to another program, it's terminated immediately. It's not allowed. So the memory manager needs to know every command that's issued to change memory, where is that program? Let's say this is program number 1, wherever it is. It's size 60K, but it starts at this location. This is the address, whatever the address was. So it knows from this point to that point, any command to change memory, it will say, what's the address of memory to change? It will find the address, and it will make sure that address is between this point and that point. That's okay. If it finds that this program is trying to modify memory outside its boundaries, it will terminate it. It's not allowed. Especially if it tries to change something in the area that belongs to the operating system. That's a big no. Okay, so that's something you need to know, that every program is allocated a certain space in memory and can only modify the memory in that space while it's executing. If it tries to modify memory outside its bounds or outside its limitations or addresses allocations, then it will be terminated. Okay, let's get now to the other point. This is called the dynamic partitioning system. The difference between this and the fixed when they start. Let me go back to the fixed just to show you where at the start, initialization. This is when you switch the computer on and the memory manager is told, here's your memory, go and do what you like with it. So first thing, before any program comes in for execution, the memory manager will take the memory and allocate the part of it, where is the operating system, where is the last memory address used by the operating system, and start from this point onward. Start dividing this into variable size blocks. And the idea, they're different size blocks. So if it gets a big block, if it gets a big program, it'll try to allocate it a big block. If it gets a small program, try to allocate it into a small block. So hopefully it'll accommodate everyone. So that's what it does initially. When the computer is switched on, the memory manager will mark the area that belongs to the operating system and break the rest of the memory into separate blocks and put that information in a table. So it knows each block free and how big it is and where it is in memory. Now, the dynamic works slightly different. The dynamic memory management system, when it starts first, it marks obviously the area that belongs to the operating system. And starting from this address, it puts the entire memory into one big free block. So it marks just one big free block. That's how the dynamic works. So it's even easier. It says, how much memory do I have? For example, 16 megabyte or 16, whatever it is. Okay, now I have one huge block. That's fine. Now, when a program comes in with the fixed partitioning system, the old system we looked at, a program comes in, it says, I need 25. All we have to go through the table and find a block that will accommodate it, and that's free, and we will allocate into that place. With the operating system, with the dynamic partitioning, says, let's find a block, or we have a big block that will accommodate it. Let's say a program says, I need 25. We go there and we break exactly 25K. This program number one needs 25. We give it exactly 25. We cut off, we mark from this address. Let's say, for example, this address is 10,000. You need 25, then you end up, you're allocated from 10,000 to 10,025. Guys, if you keep on talking, I'm going to ask you to leave. Please. This area here. Please, stop talking. Now another program comes in that needs 178K. Program number 2. So now remember, we have 2 blocks. One is busy and the rest of it is free. And it's a huge block. So we, starting from this point, we find exactly, we add to it 178. And at this point we say, that's it. We give program number 2 as well, exact amount of memory, which is 178. And this is busy and that's busy. And then another program comes in that says, I need 50 or 49. We can give any value. So this program needs 49K and we allocated 49K. Program number 3. And then this program needs 17K, for example, another program number 4. Just one last program here. Program number 5 needs, I don't know, 320K, 321K. So we give it 321K, and these are all busy blocks. Now, when does the problem start? Well, there's no problem so far. So far, it's extremely efficient. There's no internal fragmentation. You remember internal fragmentation?
Yes.
How does internal fragmentation happen?
There is a space in memory that is not used by the program.
Yeah. Put it in fewer words.
When a program gets a space larger than it needs.
Yeah. When a program is given or allocated space or a block bigger than it needs, that it will have internal fragmentation. It will have extra space it does not need. In this new system, that problem is removed. There is no internal fragmentation. No program is given one more byte more than it needs. It's given exactly as much memory as it needs. Let's carry on and see how operation happens with this one. Let's say now program number 3 finished. So you don't know which program is going to finish first. So let's say program 3 finished. So this block here is free now. How big is it? 49K. P3 is not there anymore. So now we have 2 free blocks. This 49K and the big one, the rest of memory. So now you're going to start a list of free blocks. You're going to have blocks now from now on. Each one of those is a separate block. Let's say now this first program number 1 finished as well. So this block is free as well. This is size 25, this is size 49. Are you following me, guys? Now, let's say we get program number 6 and it says I need 47K. How do you think we'll allocate it? Any idea? We go through the blocks. This one is free, but it's only 25. It won't fit it. We go to the next one, and here's another one free, and it's 49. Will it accommodate it? Yeah, but remember, we don't give any more than it needs. What do? We cut exactly 47 here, which breaks this block into a free block of 2K, and now program number 6 is sitting here. So program number 6 gets exactly 47K, but we're left with 2K. 2K is useless. It's no good for any program. But it doesn't belong to any program. It's free. It doesn't belong to no one. It's like having a little room that doesn't even have a bed in it. It's just a chair or a couch or something like that in a hotel. It's no good. And if it's no good, then we call it's another fragmentation. This is a different problem. But they call this external fragmentation. Remember the the fixed partition, the previous system didn't have external fragmentations. Any fragmentation was internal. We give you more than you need. So that fragmentation belongs to you, even though you don't need it. So they call that internal fragmentation. But this one, we actually have a free space that belongs to nobody. We can use it if some program can use it, but it's too small for any program to be used, and we call it external fragmentation. So how does external fragmentation happen? If for example, first if you're asked, right, what's the difference between internal fragmentation and external? Internal fragmentation is if you have space that you don't need it. How does it happen? If you need certain amount, but we give you a bigger block than you need. We give it to you, you don't need it. That's called internal fragmentation. But external, in this system, in the dynamic, we never give a program more than it needs. Every program gets exactly what it needs. So external fragmentation is a small amount of memory that's too small to be useful for any program. So it's just useless. It's like you build a house and your neighbor builds a house. There's this space between the two houses. It's external fragmentation. It doesn't belong to this neighbor, doesn't belong to this neighbor. Nobody can use it, but it's useless. Nobody can build a house and there's only that gap. So it's called external fragmentation. It's called external because it doesn't belong to anyone. Fragment because it's useless. It's too small to be used. How does it happen? Here's another example. We get another program. Let's say we get another program that says, I need 315 kilobyte. So program number 7 needs 315. Oh, sorry. Before that, program number 5 finished. No. Let me make it more realistic. First, program number 7 comes in and says, I need 50K. Do we have 50? No, we don't. So we go down, that's too small, that's no longer free. So we come down here, we go to the big block and we take 50K. So this is program number 7 that has 50K and it's busy and the rest of it is free. But now program number 8 comes in, or program number 5 finishes. Program 5, finish, end. So we go down, this program finishes, it's gone, and we mark the busy, it's been free. So we have now 25K free, we have 2K free, and we have 321K free. So now program number 8 comes in and says, I need 315K. So we go down, that's free, but that's too small. That's free, but that's way too small. That's free. It'll fit 315. So we'll chop 315 out of it. So that leaves us with 6K free and 315 busy for program number 8. Okay, do you see how it works? Now that's what's left there. The 6K is probably internal fragmentation because it's way too small normally for a program to use.
External.
Okay, yeah, external. So I was just testing you again. So is the 6K internal or external fragmentation before you ask the question? External. Yeah, so what's your question?
Can the memory go just combine like 325K, 36K?
Yeah, that's okay. Yeah, that's very good. That's what they actually done as part of the deallocation. So far we've been allocating. So when the programs continue, so when it starts first, it's the most efficient system. There is no wasted space. But then after a little while, as programs start finishing, we start having free blocks in between, busy blocks. And when new users, more programs come in, we start cutting those free blocks into even smaller blocks, and we start getting a lot of fragmentation, a lot of external fragmentation. So there was a question in the exam, how does internal fragmentation happen in fixed partitioning? In fixed partitioning, anybody cares to answer? How do we get internal fragmentation in the older system, the fixed partitioning? How does internal fragmentation happen?
When we have more memory than
Yeah, if you allocate a program a bigger block than it needs, it will have spare memory, and that's called internal fragmentation. How does internal fragmentation happen in dynamic memory? how do we get internal fragmentation in the newer, this system here, the dynamic? Anybody wants to answer? How do we get internal fragmentation in dynamic partitioning? There is no internal fragmentation. We never have internal fragmentation. So in dynamic partitioning, we solve the problem of internal fragmentation completely. We never get it because that's how it works. You want 12, we give you exactly 12. You want 29, we give you exactly 29. We never give you more. But the problem now with this system, we're starting to have lots of small fragments that are useless. And sometimes a program comes in, like all our memories now is almost busy, but we have lots of internal fragmentation. We get a program that says, I need 60K. And we have 200 free K, 200K of memory that's free, but they are not in one big block. So we cannot even accommodate the 60K program, even though we have 200K. But what we have is lots of small fragments. They are no good. Okay, so sometimes this system became inefficient or has a problem. Is that because we can have lots of memory free, but it's not in one continuous block. It's in small fragments, which cannot be used. Yes, that's so. So what they started doing with this system, they say, every time a program finishes, so that space becomes free. Check this, the block immediately before it and the block immediately after it. If either one of them is free or both of them free, join them into a bigger block. So like this, what happens? Let's say this block number 2, that's program number 2 finished. So this block here became free. So this is the deallocation. You know, what does the program do? In the fixed partitioning, we said all you have to do in the deallocation, you go to that block and mark it as free. That's it. This program finished, we mark this as free. It's just like a room in a hotel. Mark it as free. So if someone else comes in, we can allocate it. But in the dynamic, what happens now in the dynamic? You say, go to that block in the table, mark it's free. But then look at the block above it and the block immediately after it. Are they both free? Here, the one after it is busy, so leave it. But the one before it is free. So let's join those two free blocks together into one single block. Okay, do you see the idea? It's like you have two rooms, one next to the other, and you knock the wall between them. So now you have a bigger room. You have one room, but it's bigger than the two of them. How big? It's the size of the first one plus the size of the second one. So in this case, we have a block here that's exactly 25K, it's free. And this block is 178K. So we join them into one block. So how big is this block gonna be? 178 plus 25. What? Pardon? 203? So now the new block is gonna be 203. So this is part of the deallocation. So to deallocate, in the old system, there's one step. You go and mark that room's free or that block's free. But in the dynamic, you go and mark it free and then check. Is the one before it free as well? And the one after it? If not, if they're both busy, leave it. That's all. You can't do anything. But if the one before it or the one after it are free, or the two of them are free, so any adjacent blocks, and they're all free, merge them together into one single block. You understand that? Yeah? Are you with us or? Okay, so now that's deallocation of dynamic memory management system. Hopefully that will remove those fragmentation and will allow us to gain back some bigger blocks. And remember this one here, the one that had a little fragment there. Imagine, okay, now we have this one single block free. This is busy. Program 6 is there. And we have now the next fragment is free of 2K. Let's say this program finished. This is block. This block here that had program 6 is now free. Program 6 just finished. So we go and mark it as being free. So this is free. The one before it is free and the one after it is free. See that little one with 2K. So we have 2K, 47K, and 203. You can merge them, the three of them together into one block. How big is the new block going to be? So 203 plus 47, that's 250 plus 2. So now we have one free block from here to there, somewhere here, and it's 252K, and it's all one block and free. Okay, so this system starts with one big free block and allocate every request exactly as much as it needs. As programs finish, they start marking their space as being free. And if there are two free blocks adjacent, they have to be immediately one after the other in memory, then they're joined together. And we start forming big blocks again. Now we can accommodate even smaller blocks and so on. Okay, so this is the dynamic partitioning memory management system.
So they do have to be cited, like right next to each other.
Exactly, they have to be. In order to join them, they must be. So if they're not, we'll leave them. So you could end up having big block here, a program or two busy here, and then another few blocks joined into another one single block. And what they do, in fact, they do keep two tables, not like the previous system. They need two tables of memory. One table of the busy blocks of memory and one table of the free blocks. Obviously the busy, each block is how big it is, the size, the address, where it is in memory, the size, and who is there, which program, the process occupying it. The other one, the free ones, each one, we know they're all free, just the address and the size. And if a block that's busy here, we move it to the other table. And we find it, oh, it's the one before it is free, we join them and merge them into one single block. So this has performed better than the fixed partitioning. The fixed partitioning is easy to program for programmers, easy to implement, but it suffers from a problem. See, this system here that we call the fixed partitioning had major problem. Anybody remembers what the major problem is? Internal fragmentation. So the newer system solved that problem. We don't have, in the dynamic partitioning, there is no internal fragmentation, but we have another problem or disadvantage. Remember what it is for the dynamic partitioning? External fragmentation. How does how does internal fragmentation happen? That's the easier one. Anybody want to tell me how does internal fragmentation takes place? Yeah, if we give a process that needs certain size, we give it bigger storage than it needs. Then any extra space there, we call it internal fragmentation. How does external fragmentation happen?
When does a small amount of memory
And how does it happen? You gave me the definition of external fragmentation. It's part of memory that's small, that's too small to be used. But how does it happen?
When the programs finished working and they so there's a lot of free space, but it's so small. There are small fragments.
How do we get a small fragment? How did, like, there are loads of small fragments, but looking at one small fragment, how did it happen? Oh, thank you. No, how does one in external fragmentation takes place?
Because when the first program occupying the complete space is finished, and the next one being allocated to this space, but it has like its own size that's different. So this difference is kind of became little free fragments.
Okay, anybody else want to have another attempt? How do we get external fragmentation? How does it happen? How do we end up with 2K or 7K or something small?
And finished. Now I have a 22 program. You allocate the memory and we have 22.
Yeah. If we have a free block of memory, let's have an example, 100K, and a program comes in and says I need 99K. We cut off 99, what we are left is with 1K. So external fragmentation happens if a program is allocated space from a block of memory that's a small bit bigger than the actual program requirement. Example, a program is, a block is 100 and the program needs 95K. So we cut 95K, we give it to our left with 5K, that's called external fragmentation. Internal fragmentation, if we give any program a block that's bigger than the program needs, or any space left, it's called internal fragmentation. But this system, guys, it still suffered from very many external fragmentations as it keeps working. And sometimes a computer in the old days, and even today's, it might run for a number of years. They never switch off those computers. Like computers in big organizations, they could run for 3, 4, 5 years. They never switch them off. They're always constant. More programs coming in, executing, they finish. Some programs finish in few seconds, some programs finish in minutes. Some programs will probably run for hours or continuously based on, events that happen. But some computers, they actually never switched off. But what happens they found as computer kept on working, they just start getting more and more fragmentations. The ones that finish, they don't always join together because they are not next to one another. And therefore, they improved this system a little bit by calling it the relocatable relocatable dynamic memory management partitioning system. So it's same as the dynamic, but they just added another step to it. Kamush, guys. Okay, let's look quickly. How does it work? It's the same as the dynamic. And let me just take just a snapshot of the memory management system of some dynamics. All right, so let's imagine this. So this is a free space. That's another free space, that's another free space, that's another free space. They're not next to each other. The rest of them are busy blocks. So this is busy, 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 and busy. And you can have thousands of fragmentations. And sometimes You get you need a program that's 60K, and you have plenty of space memory because you know your total memory, you know the total programs that are running. You should have, 5 million bytes of memory. But you get a program that's only 500K, and you cannot run it because you don't have all this, because there's lots of fragmentation. So they said every now and again, and we'll find when it's a good time, to do a relocation. Relocate all the programs, move them to one side of memory, and all the free blocks to one side of memory. So the busy blocks are moved and the free blocks are moved to the other end, and we join them together and we end up with one big, hopefully, free block of memory. So, on hard disks, I don't know if you ever heard of it, they call it defrag on a hard disk, but that's on hard disk, a different. So, what does this mean? It means move all the free blocks upward in this particular example, and move all the free blocks downward. It takes a bit of time, even though it's main memory and it's fast, but still you have to stop executing and you have to move the programs around. So hopefully this memory, same programs, will look something like this. Let's say this is program 1, this is program 2. Now program 1 is there, we did not move it, but we brought in program number 2 there, so program number 2 went there. Of course, this fragment is moved down, and then we moved, this is program number 3, which is a small one, but there it is, program number 3 is busy, and then program number 4, which is fairly large piece of code, program number 4 is also moved up, and then program 5 is also moved up. Now you have lots of free fragments, that one, this one, 2, 3, 4, 5, and here they are, 5 free fragments of memory. They could be 50. Now, because they are one on top of the other, immediately one after the other in memory, we can merge them, the actual, it's called merging, is the process of merging free memory, and they're put together into one big free block. So it just becomes a free block for the whole lot. And this process, it's called compaction. So compaction is like organizing things very tightly. That's what compaction is, the word. Compact, that means, for example, if you have lots of furniture or tables or books, you put them one next to the other, so you have more space in the other side. So compaction is putting all the busy blocks, one following the next to each other in one end of memory. When I say one end, from an address point of view, remember memory is address 1, 2, 3, 4. So we know where does this one start and how big it is, and we know where this one starts and how big it is. But we need to copy all the code that's in there, put it up there and move it, without, of course, losing any data that belongs to any program. So now we end up having all this part here is busy and all this part here is free. This is the compaction operation. It happens on hard disks, but they call it defragmentation. They call it the real name, defrag. I don't know if you ever done it on a hard disk. In order, remember when your files and your data is stored on the hard disk, they're not stored continually. Not every file is put in one block. Every file probably is split into 100 pieces in different parts of the disk. It's a little bit difficult for the disk to read it sometimes, slow. And you want to maybe store another file, and they tell you we don't have space. So they do that on hard disks as well. You can do it on your hard disk. And that operation is called defrag. You move all your files on the hard disk, pack them up nicely. It makes your computer reads and writes quicker to the files, and it gives you a lot more space. But it's a similar, but now we're talking about memory, and in memory it's called compaction. And compaction is a function that's now synonymous with this system. It's the dynamic system, but the new modification of that's called relocatable dynamic. So the relocatable dynamic is an improvement of the dynamic system, and it has the extra function that's called compaction. What does compaction do? Anybody can, you know now what it does, but can you put it in fewer words? What does that compaction function do? Or why should we run this compaction function? We run it, say, every 6 hours, or we find out when we run it, maybe once a day.
Compaction runs all the big blocks
blocks
together.
next to each other. Like putting the BG blocks.
Yeah, okay, forget about the details, give me the overall thing. When you run it, what happens?
Like it will organize all the BG blocks next to each other, and the tree will be at one location.
Yeah, okay, so it will organize the busy blocks to one end and the free blocks to one end. What does that give us? What's the the outcome of this function? We will have one big block, so it actually gets all those fragments, put them together into one big block. So they say it reclaims the fragments, the external fragmentation, and make use of it, a better use by having it into one big block. But this compaction function, guys, is a slow, very slow. Even though it's done in main memory, it's still compared to main memory, it's slow. And when it's being done, there's no execution, you have to stop. Maybe it might only take a few seconds, but few seconds in CPU time is, it might even actually reach 30 seconds of no execution. That's a lot of wasted time. It's not a good thing to run. So when would you run it? When would you recommend to run it? You can't say let's run it every hour. That's way too expensive. It's not efficient. When do you think we should run it? Some people say you should run it when we are not busy, when we have very few programs executing. No, but we don't need it at that time. You actually need it when you have lots of programs executing and lots of fragmentation. When do you think we need to run it? Is when you start getting requests. I see hands going up. Do you want to answer? Yeah?
When a big chunk of the memory is not being used, so the machine is not efficient because of the...
How do you know it's not? When do you know that?
Like
what
10%,
signal or sign will
like
give you that?
10% of the memory is not being used because of fragmentation, something like that.
Yeah. Okay. Yeah.
When you're waiting for user.
When?
When you're waiting for user input.
No, the program still in memory until it finishes completely, not just when it doesn't use the CPU. A program is still executing when it's in memory, even if it's waiting for an input or an output, because somebody's doing their input or output on their behalf, they're just waiting for that. Now, a program stays in memory until it actually finishes completely, and that's when we take it out and we mark the block as being free. But when do we think, we say, guys, maybe we should run this defrag?
Maybe when we're kind of running out of space, we notice that our space is almost reached limit, we combine it much more efficiently. Hard drive, for example.
Say again? No, let's talk about memory now, just in case we get things. Yeah?
Maybe when we're reaching the limits of memory, we just run
How do you know what's the limit? You only know, you can find out how much memory you're using because your programs, you know how big the programs are, and the memory manager always keeps how much of my memory is being used. I have 10 programs running, let's say if one of them is 100, so 10 times 100, it knows 1,000 bytes of my memory is gone. I have another 1,000 bytes free. Okay, so if you know you have 1,000 bytes free, and a program comes up to you and says, I'm 60 bytes and I have a memory, you say, no, I don't have memory for you. Even though you know you have memory, you have 1,000 bytes free, but you cannot allocate memory to this program that only needs 60. Why not? Because you have fragmentation.
just in case we should use this fragmentation compaction.
that's when you should, or you think now it's good time to run the compaction function. That's kind of a signal, an indication that, hey, you probably have a lot of fragmentation. So that's how you'd know it. There's no other indication other than, you know, how do you know you have a lot of fragmentations? Maybe if you have a large number of free blocks, if you keep the number of free blocks, but a good indication is you keep getting requests for programs to run. They're small programs, and you look and you say, I have plenty of memory, but they're sitting waiting to start executing because we cannot give them a block. That means if we have a lot of blocks, or if we have a lot of memory, but we cannot run a program, that means our memory is not in one big block, it's in lots of fragments. That's maybe a good time to know, hey, we need to run this compaction function. So in general, guys, the compaction function is slow. You don't want to run it continuously or every time. You try to minimize. You say, no, I better not run it, because if you run it, you're gonna stop executing. That's one thing, for a little while. So it's slow operation, but also, remember, when you move a program from one place, remember, you always have a table. I mentioned it earlier on the dynamic. You always have a table of where each program is in memory. You always need to know where every program is and how big that program is. That means it has a limit from this part of memory to this address. Between those two addresses, that program can work freely. But now if you move this program somewhere else, you're after changing the limits, the boundaries for that program. And you need to correct that. And that's another little problem that's added by the compaction. The compaction, it's slow to work, but it also will move programs from one place to another, and you need to adjust the limitations. Remember, every program, this is something happens so quick that if a program say execute, put 5 in X, it says, where is X? And try to get the address of X. Now, the number will say, is this address of X, is it between the minimum and the maximum addresses that we gave this program? Now, we're after moving those addresses. So we need to make this correction. So this correction, and you can't just start changing that, but their correction is they add another relocatable value. For example, just get an example and we'll stop at this point. Let's say this program number 3, for example, it works at location, for example, address 14,000 to 15,000. Okay, so that's in memory, it's located between 14,000 and 15,000. Now, if it gets, say, put this value in X or Y or whatever, it wants to change memory or read memory, we have to get the address between 14,000 and 15,000, or else if it tries to change anything outside its boundaries, these are called boundaries. The bounds of this program. Every program has memory bounds. That's limitations, addresses. Let's say 14,000 and 15,000, and they're written somewhere in a variable. The upper limit and the lower limit. Now, let's say we just move this program somewhere here. After compaction, we move the program, move down here. And instead of 14,000 to 15,000, now it's 10,000. It starts at 10,000 and ends at 11,000. And now it says, modify this X, whatever address, and it's 10.5, 50, 10,500. So it wants to change the address somewhere here. Now, the limits that we had for it already written are 14,000 and 15,000. Now, what they do is they have another address, and it's called relocatable address. So you move this program from 14 to 10. So you moved it upward in memory 4,000. So they give that minus 4,000. So now any address that's generated by that program, subtract 4,000 from it. Because the program would be normally, we don't change the original way the program is, but we give a correcting kind of relocatable address. So if the program initially said, move this address location at 14,500, that's okay here, but after moving it, 14,500 is not good. So here's the address that says, change this location address. We say subtract every address generated by this program from now on. We're gonna remove 4,000 because we moved it up 4,000 bytes. So this here will be 0005 minus 0, and 4 minus 4 is 0, 1. So it's 10,500, and that's exactly now it's okay. Right? You see this is the new address that will be allowed for this program to operate in. So we have some kind of correcting address. We call it the relocatable address. So every program now, if we move it up, we have to give it a minus number. If we move it down, we give it a plus number to indicate its new location. And we don't stop it later on from working. So these are 3 memory management systems. They are not used today, but tomorrow or on Friday, we'll carry on and we see how today's, they call paged memory systems and virtual memory systems, how they work. But just a quick revision. We start with memory. We started with the fixed partitioning system. You need to have a good idea, be able to answer questions. Once you understand how it works, you should be able to answer any question. But generally, you're asked how to describe fixed partitioning system. Try to describe, if you are asked to explain it in, detail, what happens at the start before any programs come in. When we switch the computer on, how does it prepare memory? And then when a program comes in, what happens? That's allocation and deallocation. So fixed partition memory management, you could say when the computer is switched on, part of the memory is allocated to the operating system. The rest of the memory is prepared by breaking it into different size blocks. Why? So if we have a big program, hopefully it will fit it into a big block. And if we have a small program, we try and fit it in a small block. To allocate, we just search through the list, put the program in a block that will fit it. To deallocate, all you have to do is mark that block as being free. The next system we talked about is the dynamic partitioning. How does it work? When we start first, part of memory is allocated to the operating system. The rest of it is kept in one big block, one big free block. And now, if a program comes in, we allocate it. We cut exactly as much, the exact required memory by every program. So a program comes in, needs 17K, we cut 17K and allocate to 17K. When a program finishes, we do the deallocation. What does the deallocation involve here? First, we mark the block as being free, and then we try to join it to the one before it or after it or both, or merge it, the word that's used. If the block becomes free, we look at the one before it. If it's free, we'll merge them, and the one after it, if it's free, we'll merge them into one bigger block. Problems still consisted or continued with having external fragmentation. Then we use relocatable dynamic, where we use a function called compaction, and it just tries to recover all the fragments, external fragments of memory. How does it do it? Stop execution, try to move all the programs to one end of memory, one next to the other in their blocks. You move the program blocks and all the free blocks to the other end and merge them together into one big free block. The fixed partitioning system, that's the first system. It's the easiest to implement. So simple, but it suffers from internal fragmentation. It's not efficient at using memory. Dynamic partitioning system, it's better that it has no internal fragmentation, but it suffers from something called external fragmentation. Compaction or relocatable, it solves the problem of external fragmentation, but at a high cost. Very slow to run. Any questions? I asked a few questions there. Now I can see the questions.
Can you repeat compaction once again?
Hold on, one at a time.
Can you repeat compaction once again? Compaction.
Just 1 second. Right, what's the question? I can't hear you. Hey guys, please be quiet. Because if you are moving a program and the CPU tries to execute it, you are moving its location. And see the way the CPU works, it says, get me the next instruction. If you're just after moving it, you can't do it. You cannot execute and move the program at the same time. You have to wait till the program is moved. Any other questions? Compaction is, memory is gonna be split into blocks. Busy blocks and free blocks, busy blocks and free blocks. Compaction is moving all the busy blocks next to one another and all the free ones next to one another, with the aim that all the free blocks that are neighbors, immediate neighbors, we merge them into one big free block. Okay? Any other questions? What's the disadvantage of dynamic partitioning system? That's the second system, not this one, the one before them. This system, what's the dynamic partitioning system? What's the major problem with it? Yeah? I can't hear you. It suffers from external fragmentation. Is that what you're saying? Okay. And what's the disadvantage of the fixed partitioning system? The first system we talked about. It suffers from internal fragmentation. How does internal fragmentation happen? These are exam questions, guys. Simple questions that require 2 lines or 3 lines of answer or diagram or something, yeah? How does internal fragmentation happen? If we allocate a larger block to a program, that doesn't need the entire block, it only needs part of it. Whatever is left is allocated in the program, but it's extra, and therefore it's a fragmentation. How does the dynamic system get rid of fragmentation?
Every once in a while, when it's run out of space, it stops everything.
No, okay, just one. Are you going to talk about the compaction? That's in the relocatable dynamic. That's in the next system. This system alone, the dynamic that does not have compaction. How does it actually eliminate? Yeah, no, external fragmentation. Like we're going to have few fragments every now and again.
It doesn't move them, but if they're right next to each other,
it uses the merge. During deallocation, it marks a block as being free, but then try to merge it to the one before it or after it or both of them. So sometimes 3 blocks are merged together into a bigger block, and that's how it tries to get rid of external fragmentation. How does the relocatable one remove external fragmentation? Okay, by using the compaction function. When do you think we need to run that compaction function?
The program like allocated, the busy programs are separated from the free ones and they are moved to one end.
You hear that? Was it a good answer? Yeah, good answer. Good, thank you. Okay, any more questions, guys? Now, you want to hurry to go? I'll ask you a quick question and then we go. Attendance, does anybody has any problem with attendance? Okay. Thank you guys, and I'll see you Friday.